During this session, the third lecture session, now we'll continue our the discussions on theory of constants. We have already discussed some so the basics of the theory of constants methodology, and slowly you are your understanding that what are the basic focus, what is the basic objective of implementing theory of constant say the methodology in a manufacturing system. So you have come to know what is actually the bottleneck resource, what is a non-bottleneck resource, how can you establish the relationship between the bottleneck and the non-bottleneck resources, and how to link them with the other aspects of the production systems. Now here during these lecture sessions, some other the concepts we are going to discuss related to TOC. The first one is the process and transfer batches. Everyone we are all aware of the batch size as it is produced in a particular work center or a resource, and so this is referred to as the process batch size. Okay, and determination of batch size, there could be several approaches. There are several the formulae you can use, so you are all aware of. And so but here we are also defining another term related to batch formation, and that is referred to as the transfer batches. And so the process and transfer batches, their definitions, and why do you go for such differentiation for in respect of TOC. So that point will be discussing in details. Then we face a problem like, say, always it's a dynamic situation. That means determining the actual requirement at a particular stage, say it's a real problem. And the main reason could be that the dependency between the different stages. So the modeling of dependency is not that easy, and that's why many a time you go for online real-time control system. So day-to-day monitoring, hour-to-hour monitoring is the alternative. So the dependent events it should be considered specifically, as well as the statistical fluctuations. That means the demand is changing, say, and at a very there's a lot of variability in the demand. So while you make a robust systems, a control systems, so that is your goal through the TOC. So how to take care of the statistical fluctuations. Then the third important issues we are going to discuss, that is the capacity constant resource. So how do you define capacity constant resource, and why do you define it, why you try to identify it? And one point you just make a note, that is this entire the exercise of TOC that starts from identification of the capacity constant resource, in short CCRs. So among say the resources, you need to know what are the capacity constant resource, and then only if your definition is clear and well defined, and then only it becomes easier for you to initiate say the actions or to initiate steps for implementing TOC methodology. And then towards the end, when we have sufficient knowledge about or you have developed the concepts, what is it and actually with respect to the TOC, then you should be aware of what are the specific the TOC principles you must be able to follow. Now the TOC defines two types of batch or the lot sizes. This term is already familiar with, the lot size, like production lot size, okay, or say the purchase lot size. Process batch and transfer batch. So what is a process batch? Now a process batch is a production quantity of a product at a resource against a setup. We have already discussed that against the setup, okay, you have you determined the production quantity, say 500 against one setup. So if you so if 500 units are produced, what you need to do, that means you need to set it up once again. Is it okay? So so that you can maintain the quality of the units within a particular batch. So this is the basic the principle we follow. So against a setup, the batch size is known for a particular process, and that's why it is referred to as the process batch. So process batch determination is a must first. Next one is the process batch can be split into the several transfer batches. That means a transfer batch is a quantity of units transferred from one resource to the next while the production of process batch is on. So what does it mean in plain and simple terms? It means that suppose you produce the 500 units in 4 hours. So so one approach could be that first you produce 400 units in 1 hour, say in 500 units in 4 hours, and then once the 500 units are produced, so you send these 500 units in one shot to the next stage. So that is the approach. So obviously the flow is disturbed. That means during the time you are producing these 500 units at your process, the next stage, which is dependent on you, so it is waiting for this. That means the 4 hours it may not get any the units to be processed. So the flow is hampered and there will be discontinuity in the flow. So in order to avoid that, what you try to do, that means suppose the 500 units you produced in 4 hours, so on an average 125 units you produce per hour. So as soon as 1 hour is over, so you have with you 125 units. So why don't you send it to the next stage? So this is referred to as so the transfer batch. And if you can reduce the transfer batch size, obviously the continuity or the flow will be more smooth. Is it okay between the workstations or between the stages or between the processors? So this is the basic idea behind the splitting the process batch into several transfer batches. So a transfer batch is the quantity of units transferred from one resource to the next while the production of the process batch is on. Is it okay? A transfer batch is less than the process batch. Is it okay? It should be substantially less than the process batch. If you can do that, if your system permits it, then you will find that the entire material flow becomes much smoother. And this transfer batch should be small as possible to maintain continuous flow of parts and products between resources. A non-bottleneck resource has idle time because its capacity is more. A process batch at a non-bottleneck resource is less than that of a bottleneck resource it feeds. Is obvious. So just you go through the statement, you find the logic is made very, very clear. Is it okay? Because you activate the non-bottleneck resource as per the requirement of the bottleneck at a particular point in time. That means both the quantity as well as the timing you should mention. Is it okay? The timing of production as well as the quantity of production. So these are the two important aspects you need to look into when you try to describe the relationship between a non-bottleneck resource and a bottleneck resource. Now the process batch at a non-bottleneck resource should be as small as possible, almost equal to transfer batch. Is it okay? So means the flow of material from say the non-bottleneck resource should be as restricted as possible. Is it okay? And absolutely it should match the requirements of the bottleneck resource with which it is linked. And when you say it's matching, that means matching with respect to the quantity and matching with respect to the timing. So please note down these 2 points. That means whenever we talk about say the TOC based scheduling, this is essentially we are referring to scheduling. 2 important aspects you must look into. One is the quantity, okay, matching with respect to the quantity and matching with respect to the timing. Now transfer batch from a bottleneck resource should be as small as possible so as to avoid discontinuity in flow of materials, parts, products. Okay, a small transfer batch reduces throughput time significantly. Okay, particularly when there are large number of parts processed. It means that what happens if you maintain the continuity. So obviously if you try to maintain the continuity, that means you don't need to wait for processing. That means waiting time will be less. And similarly, the transfer, that means the transferring the batch. So here essentially you need many a time you need appropriate material handling systems. And the advantage is if your the transfer batch size is less, now even the manual material handling is possible, and plus even if you use say the PIT or say like say the powered industrial truck. So the smaller size of the PITs you can use for transferring say the lot, that means the transfer batch from one unit to another, from one resource to another. Is it okay? So in the process what happens that the proportion of the non-value adding activity is reduced, whereas the proportion of value adding activity is increased. So throughput time is significantly reduced if you apply this concept. Okay. So a process batch may be a variable along its route and over time. So this is when you consider a number of say interconnected the production stages or the processes in a manufacturing systems. So obviously the process, there will be a variable, the process batch from say the process A to B, it could be 25, from B to C it could be 20, from C to D it could be 50. Okay, so it's a variable along its route and over timing. Is it okay? That means in the same so the between A and B, so the first hour the process batch could be 50, in the next hour the process batch could be 75, the third hour it could be 60, and so on. Okay, so this is the meaning of this particular say the statement. That means a process batch may be a variable along its route and over time. If the classical EOQ, actually what is the classical EOQ formula. So the classical economic order quantity does not consider the types of resources. This is a severe limitation. This is one limitation of say EOQ, as if EOQ is applicable for all kinds of resources and is not applicable in TOC. Just make a note of this particular comment. Cost-based approaches without considering throughput may lead to system sub-optimization. So this is another say the important statement, That means definitely the cost-based approach is applicable, but you have to go beyond the cost-based approach, so that the other kinds of benefits also you get, particularly when you talk about complex systems, so the scheduling for a very complex systems, repetitive manufacturing, discrete part manufacturing, and the dealing with hundreds and thousands of parts. Okay, so these are very complex situations, and you come across several types of constraints. So what they have found, the practitioners, that the TOC has high level of applicability for such cases. Okay, and what is most important is, as per the systems theory, we say that the subsystems optimization, okay, the sum of subsystem optimization, okay, doesn't necessarily mean that that you will be getting a total systems optimization. Okay, so this is so it talks about, so it is systems theory is applied in TOC. Now there is the two aspects, dependent events and statistical fluctuations. So let me just explain it. The concept is very simple. These two factors make a condition, smooth and continuous flow of products matching with the demand, difficult to achieve. So you have just one specific objective in TOC. What is that objective? Smooth and continuous flow of products matching with their demand. This is your say your main goal or the main objective. Now this objective may not be able to achieve fully if you do not have sufficient control on these two aspects. So the first aspect is the dependent events. So what is it? Products are produced in a sequence of operations, and these operations are dependent on one another. Like when we refer to a process plan for a particular product, obviously there is a sequence of operations. So this is that means there is a dependency between the operations, or two or more products may need the same operation. Okay, so this is also so it is also referred to as the dependency condition. So the dependency condition is unavoidable, you cannot avoid. Then the next important aspect to be considered, that is the statistical fluctuations. Variability in a process may lead to variability in output or outcome due to several reasons. Okay, so the variability study is an important study, not only in quality, okay, but also for in production control systems, when you study production control systems, or when you study in inventory control systems. So so the variability is important aspect, and the time variability in human activities. So this will have an effect. Absenteeism, breakdown, non-supply of materials on time, etc. So these are the factors. Actually, it creates, or it leads to it the and it's the create variability in output or outcome. Okay, so you can identify several such factors when you study a particular system. When you start collecting data, obviously you will come to know in a specific situation what are the specific factors, okay, resulting or say the leading to or the affecting or say the variability in the system, so creating variability in the the system's outcome or the system's output. Both these factors may result in discontinuous and lumpy product flow. I have given a few examples. The key question is how to synchronize the flow of materials among different resources in a plant or a manufacturing process. That means the condition of synchronization, a synchronous manufacturing systems you have to create, where you get a continuous flow and smooth flow of materials. So the product flow depends on quantity and timing. In TOC, resources are classified at the next level of analysis as capacity constant resource. First you have defined resource, you know what is a constant. Now we go to we are going to define two kinds of resource. One is the capacity constant resource, and the second one is the non-capacity constant resource. So what is CCR and what is non-CCR? A resource which if not properly scheduled is expected to cause the actual product flow through the plant to deviate from the planned product flow. That means when you have to make a plan, so there must be a planned product flow. Okay, that's your starting point. Now, due to several reasons, the product flow may change. So, what is a CCR? That the CCR is a very sensitive resource. That means if you cannot properly schedule this kind of resource, immediately there will be an effect on the planned product flow, negative effect usually on the planned product flow. So you need to identify this resource, and usually not only one resource but a number of resources may be of this type, and these resources are referred to as a CCR resource. The most severe bottleneck resource controls the flow quantity, and hence not all bottleneck resources are CCRs. Okay. Non-bottleneck resources may control the flow timing, and hence non-bottleneck resources can also be the CCRs. Is it okay? There are two aspects, the timing and the quantity. Okay. Identification of all CCRs is the first step in the development of TOC in a system. So you have come to know what is the first step. That means you must be able to define the CCR, and the next step is you need to identify those CCRs in a particular plant, and then you start working on the TOC methodology. The difference between CCR and non-CCR can be explained in terms of their influence of flow control. That means material flow control within a plant in quantity and timing for product flow planning. So this is the relationship. The resources could be CCR, resources could be non-CCR. Now the resources could be bottleneck or resource could be non-bottleneck. If it is CCR and if it is a bottleneck, then the constraints actual flow in quantity and timing. Okay, that means the constraints are affecting the actual flow in quantity and timing both, whereas here the constraints are affecting the timing of actual flow only. Okay, not the quantity. And these CCRs, whether it is bottleneck or non-bottleneck, must be considered in product flow planning. So essentially the TOC exercise is nothing but an exercise on product flow planning. But if it is a non-CCR, then it may constrain actual flow in quantity and timing. Okay. And if it is a non-bottleneck resource and as well as the non-CCR, then it does not constrain flow in quantity or timing. So what is your decision? The decision is that non-CCR may not be considered in product flow planning, whether it is a bottleneck or whether it is a non-bottleneck. So my advice is you study this table intently, and later on when you get a few the practical examples, this will be made more clear. So there are now, before we conclude the sessions, I will just tell you that what are the TOC principles. Okay. So by this time, you have come across, or you have come to know, you have become familiar with several terms and terminologies, the concepts and issues related to the theory of constraints. And right now, when you have come to know these terms and terminologies related to TOC as well as the concepts and issues related to TOC, obviously you can relate these concepts with definitely the product flow planning and as well as the inventory control systems. Okay. And in general to the materials management, say the function of any organizations. So what we say that the theory of constraints is closely linked with the materials management systems of any organization. Now, what are the principles? So let me just highlight a few important principles. And so the first principle is the flow, not capacity, should be balanced. Now, whenever you talk about the scheduling systems of a production plant or the manufacturing plant, now what we are saying that you create the scheduling system in such a way that the flow of materials within the system is controlled. You don't bother about the capacity. Your first priority should be maintaining appropriate flow matching with the demand. Suppose you are maintaining the flow, but this flow, that means the quantity and timing of the flow of materials, is not matching with the demand, okay, or it's not matching with the demand all the time. So in all likelihood you will be producing non-throughput. So our the basic constant is that whatever you do, whatever may be the flow pattern, to what extent you are able to produce as per produce throughput. So that is your primary objective of creating a TOC based systems or theory of constraint based systems. So obviously even if you go for capacity balancing and the capacity is changed over a period of time, you cannot change the capacity of a resource continuously. So it is inflexible. So that's why the capacity you create definitely, but more importantly, to what extent you are taking other types of controlling systems so that you produce as per the demand at any point in time. This is your goal. And as we have pointed out with respect to the inventory control systems, there is basically the entire exercise should be boiled down to a matching systems, say a perfect matching systems between supply and demand. Now the supply is essentially you get the supply out of the production system. Definitely the production systems or the kinds of technology you use that depends on the capacity of the resource, definitely, but still when the capacity remains constant, the technology becomes constant. Now what you need to do in order to meet the demand for all the time periods, okay, you need to constantly monitor the performance of the material or the monitor the condition of the material flow all through. That means over time constantly, and that systems you must have, and there must be your system, your scheduling systems much capture the the dynamic system, okay, or the dynamic the production system. So that's why the flow essentially is indicative of the dynamics of the systems, not the capacity, should be balanced, okay. So this is point number one. The next important principle is I have already mentioned, that is an hour lost in a bottleneck resource is an hour lost for the system, which is not true. This statement, suppose if you lose 1 hour in say in a non-bottleneck resource, it doesn't mean that you are losing 1 hour for the system. So that's why the bottleneck resource should be the controlled should be controlled, and as far as possible the utilization of the bottleneck resource should be guaranteed, should be assured. Marginal value of time saving at a non-bottleneck resources is negligible. There is no point. Okay, so if you suppose you do not bother about say whether the resource is bottleneck or non-bottleneck, and you are the time saving scheme, or by by applying several the relevant tools and techniques. Suppose you start implementing for any kind of resource. So it may so happen that the effort you put for the non-bottleneck resource for time saving, now it may not have any effect on the system's performance improvement. So the marginal value of time saving at a non-bottleneck resource is negligible. And then the fourth principle is resources should be utilized, not simply activated. This is a necessary condition, but more importantly, you must be able to utilize the resource. Is it okay? That means utilization means that the amount which you can sell, and out of this sell you can get the revenue. That means you can generate the throughput, you can make money. The fifth principle is a transfer batch is necessarily less than a process batch. I have already elaborated. Sixth one is a process batch may be a variable both along its route and over time. This point also we have elaborated over the different stages and only. So the over the route, it may be treated as a variable. That means there is a change in the there could be a change in the process batch size, and over time also between the two stages. Okay. Then the next principle is all types of constraints need to be considered for scheduling. All types of constraints. That's why we have emphasized on the classification of the constraints. Scheduling process starts from identification of all CCRs. Okay, capacity constraint resource. So please you refer to its definition, and out of the resources, which one is which set or which one is a CCR. So why don't you you start modeling the scheduling system after you identify all the CCRs. So that is one of the principles you must follow. The next one is the constraints govern throughput and inventory. So we have defined throughput, we have also defined inventory. And the last principle is the constraints determine utilizations of non-bottleneck resources. So these are the 10 principles we have identified, and this is the third lecture session on theory of constraints, and by this time you have come to know that what are the basic concepts in theory of constraints, what actually you are supposed to do. And with this knowledge, once you know this set of principles, we are going to discuss the scheduling, the TOC based scheduling approaches in the next two lecture sessions, and you will find that when you discuss this scheduling, the TOC based scheduling, you will find that as far as possible, you need to follow all these principles. Is it okay? And if you cannot for certain reasons, obviously this TOC methodology is treated as a continual improvement technique. So at the next step, that means there could be a first approximation, and then maybe you are not able to follow all the 10 principles, and at the next stage of development, as a part of continual improvement, definitely you try to follow all other principles. So this process continues. So that's why it is treated as the TOC based methodology is treated as a continual improvement say the approach. So thank you.